All right, let's get started. There's still people filtering in, but I think we can get going. Um, Hi, thank you very much for joining us. I'm Nick Bray from NBA. NBA is an architecture studio based near City Hall in Vancouver on the unceded traditional territories of the Musqueam, Squamish, and Tsleil-Waututh nations. Our team's aim is to make a positive difference by creating innovative, sustainable, and community-focused buildings. Welcome back to all those who have joined our previous seminars. The intent of this series is to provide an overview of some of the recent changes we have faced in our industry today. You can access recordings of all the seminars on our YouTube channel, and we'll be sending out a link to that soon. We have two more seminars planned. Seminar 5 is on a subject that brings fear to most architects, which is fire stopping. That will be Brian again presenting that from Celerity Engineering, and that will be on May 27th. And then on June 18th, Seminar 6 will be a deeper dive into the implications of the recent seismic upgrade requirements in the 2024 BC Building Code. And that seminar will be given largely by RJC engineers. We did previously discuss these requirements before they were implemented, but now we can talk about their actual impact on current projects, specifically relating to mid-rise buildings. If you have any other ideas for seminar topics relating to issues that are currently affecting your work, please feel free to reach out to me or to the other presenters here. We'd love to keep this series of seminars going and keep it on current topics. So I'd first like to introduce Elisabeth Baudinaud from CarbonWise. Elisabeth is a principal and founder of CarbonWise, a team of energy and carbon advisors focused on both operational and embodied carbon. Her team is recognized as a leader in sustainable construction with award-winning work, published case studies, and contributions to policy and research. I'd also like to introduce Brian Fraser from Celerity Engineering. Brian has worked as a consulting engineer since 2005, originally focusing on code consulting and fire protection engineering. He is now registered as a professional engineer in BC, Alberta, and Saskatchewan, and has been a certified professional registered in Vancouver and Surrey since 2012, when he co-founded Celerity Engineering. I've had the pleasure of working with both Elisabeth and Brian extensively. And one of the things I admire most about them is their openness to sharing knowledge and information to help others grow and improve our industry and the inbuilt environment in which we live. So for a variety of reasons, as a profession, we architects, we often struggle with supporting each other and uniting in advocating for the industry as a whole. So if you haven't already, I would encourage you to sign up to organizations like the AFBC or smaller organizations like the Field Collective, who are a small network of small architecture firms in BC. Even simply connecting socially with other industry professionals, it can be a really powerful way to discuss shared challenges and explore solutions together. So yeah, I'm hoping that we can all encourage each other to work together and look out for each other. Just a couple of housekeeping items here. So thanks for everyone that's filled out the polls here. I think again we've got mostly architects, 92%, but it's great to see some other professions here as well. The AIBC accreditation form will be provided halfway through the seminar, and that will come up in the chat box, and we'll provide it again at the end. It's a very simple form. You click on the link, goes through to a form, and it automatically then provides you with those AIBC credits. So have your AIBC number at the ready. If you have any questions throughout this seminar, please fill them in the chat box. There's too many people on this seminar attending this seminar to allow people to speak. But yeah, please write them in the chat box, and we will address them at the end. Yeah, so let's get started. Please, I introduce Elisabeth.
Thank you, Nick, and welcome everyone. Very glad to be presenting here today alongside Brian and Nick on a topic that I have been involved in for a very long time. And today we'll be speaking about specifically the zero carbon step code, but I'll be starting with understanding the difference between the energy step code and the zero carbon step code. And then we'll move on to the role of electrification and the heat pump technology in meeting existing current code, but also upcoming regulations. And we'll finish with some case studies and practical applications where we'll show you some real projects that are already meeting those requirements. And then we'll end up with about 10 to 15 minutes with questions. So feel free, like Nick said, to pop your questions in the chat if you have questions along the way. So first, understanding the BC Energy Step Code and the zero carbon step code. So as you probably know, fossil fuels drive climate change. And I am always starting with this slide to kind of give some context about why the policy, why the energy step code and the zero carbon step code are in place in BC. And to help you understand, what's the timeline and what we're working with. So buildings are a significant contributor to global greenhouse gas emissions. Depending on where you look, globally, it's about 40% of greenhouse gas emissions in BC. The day-to-day operation of buildings is about 12% of BC's overall greenhouse gas emissions. So in 2021, the province released its Clean BC roadmap to 2030, the document you see here on the screen. And that's a very long document that is basically just a plan to expand and accelerate climate action to meet our 2030 target and to put us on the path to net zero emissions by 2050. So in it, there are a lot of strategies and actions, but tailored to us here is a commitment that all new buildings in the province must produce zero greenhouse gas pollution from their operations by 2030. And that's really what is driving the energy step code and the zero carbon step code. So we've known since 2017 the BC Energy Step Code, and I'll do a bit of a high level on it. But in 2023, the province entered the zero carbon step code. And that's pretty much a pathway to get us there. So local governments can now reference the zero carbon step code in their building bylaws if they wish. And it offers a new tool to help reach their climate objectives and by extension then help the province meet its own greenhouse gas targets. So very briefly, because we've all heard about the BC Energy Step Code, but just a few key things on the Step Code is that it introduced a shift from what used to be prescriptive to now performance-based energy targets in new buildings and only new buildings. So it moves away from prescriptive code and puts performance outcomes like airtightness or energy use front and center. It applies to both Part 9 and Part 3 buildings. And municipalities can choose to adopt higher steps than the province timeline based on their progression towards the end goal, which is in 2032, Part 9 buildings will all be Step 5 or net zero ready, and Part 3 buildings will all be Step 4. So the Energy Step Code is designed to align with the BC's Clean BC goals and transition to net zero ready by 2032. And it is built on measurable metrics, which you've probably all heard about, which encourage really innovation in terms of design and construction so that professionals can choose how they meet their energy targets. It is made so that municipalities can adopt at different paces, so depending on their climate, market, capacity. And one key thing is verification and testing. So now blower door tests and energy modeling are part of meeting compliance. And you've probably seen those metrics before on step code compliance reports. I want to highlight just that those metrics are interconnected. So airtightness, for example, is one of those metrics that if the building can achieve very low air tightness, then it might relax some of the other metrics, the TEDI and the MUI. So very briefly, air tightness, this is what happens during construction, as you know, so builders are liable and responsible for meeting the air tightness, but the envelope, so TEDI and MUI are both metrics that really happen or are important in the design phase. So TEDI is the envelope, and that's a metric that measures the amount of heat a building needs annually per unit of floor area of conditioned space. And in short, that means good insulated airtight walls. The MUI is related to mechanical systems. So it's a metric used to assess how efficiently a building uses energy, specifically for its mechanical systems. So it measures the amount of energy used per square foot of a building floor area per year. And that's really the choice of mechanical systems. So what type of fuel are you going to use? How big a system do you need? Can you recover some of the energy from inside the home instead of throwing it out? And this is what's guiding the energy step code with a goal of reducing energy use. Now, the introduction of the zero carbon step code came as a sister regulation because we don't want to just address energy use, but also carbon emissions. And that's why the zero carbon got introduced with new metrics, which are the GHG, greenhouse gas, and the GHGI, greenhouse gas intensity. So those greenhouse gas emissions target apply to all buildings as well, and then can be similar to the step code. Local governments can decide to implement the zero carbon step code at their own pace. And the reason behind this is because an energy efficient building doesn't mean a low carbon building. So I'm going to say that again in other words. An energy efficient building can emit a lot of greenhouse gas emissions if the energy source is high carbon. So that's why really the zero carbon step code, that's very critical to understand, is that it got introduced because we were making our buildings more energy efficient, but we were realizing that it wasn't enough in terms of greenhouse gas emissions. So what we are looking at now is not just how much energy we are using, but also what is their emissions factors. So again, a low energy building doesn't always mean low carbon. And that all depends on the fuel source. And I know terminology can sometimes be a little bit confusing, so I'll clarify some terms here. The zero carbon step code is different than embodied carbon. Another topic maybe for another day. But we have all kinds of terms out there: zero energy, net zero, zero carbon, net zero carbon. The official language from our code is zero carbon step code that regulates the operational emissions. And if you see here on a full life cycle graph of a building from raw extraction of materials to end of life when the building gets demolished and waste gets processed. So operational emissions is really what's circled there is the use phase. So every time we turn on a furnace or a heat pump or we use hot water, those generate emissions, and those are operational emissions, versus embodied emissions or greenhouse gas emissions that are embodied in the materials and processes throughout the life cycle. So it's very important to make the distinction, because there is, and I admit the language is not the easiest here, but the zero carbon step code is purely operational emissions as opposed to embodied emissions that look at materials and processes. So in the code, compliance requires energy modeling, as you probably all know, with an energy advisor for part 9 or an energy modeler for part 3. And now looks at also mechanical system design choices. And these really can make or break carbon targets. So GHGI, greenhouse gas emissions intensity, targets vary by building type and location, so it's important to know which climate zone you're working in. And now the fuel choices matter. So little by little, we are going to move away from high carbon fuels and move towards cleaner fuels, which means in Part 9 buildings, but also as a rule of thumb, like I won't go into the details of all the metrics and the numbers here, but as a rule of thumb, we are pretty much moving towards electrification. And that's because in BC, we are lucky to have a clean grid, which means that 98% of our electricity is clean, which means that when we select a mechanical system using electricity, we will emit less greenhouse gas emissions. So we are moving from EL1, which is the first step of the zero carbon step code, to EL4, which is pretty much an all electric building. So little by little, we are moving towards that. And as of March of this year, EL1 is required across BC, which means as of now, unless a municipality has implemented higher zero carbon step code levels, which is the case on the North Shore, for example, then it is just purely measuring greenhouse gas emissions. And there is no extra work involved. We as energy advisors fill out the step code checklist, and it is already part of the checklist. There is no extra work whatsoever. It is now just being reported on the compliance documents. So it doesn't change any of the processes, the modeling, or anything. But what is changing little by little, depending on where you're working, is what type of mechanical systems you'll be using. And what's really important is that fuel choices really matter, because natural gas-based systems struggle to meet the greenhouse gas intensity limit. So again, high carbon fuels will have a harder time meeting the greenhouse gas emissions targets. So electrification and electricity will be what we'll be using moving forward. And I will let Nick speak on this slide about the impact of both the energy and the zero carbon step code on project design and construction, but encouraging you, mostly architects here, 94% in the room today, that design decisions are carbon decisions. So mechanical systems, envelope, orientation, all of that impacts the greenhouse gas emissions and the metrics.
Yeah, I'd just like to add, I think that the biggest issue that we see happening in the industry relates to the starting performance assumptions. So the starting point, which is normally code minimum or whatever the local jurisdictions bylaw minimums are for the performances of buildings. Yeah, that creates a bit of a problem, because what we've seen recently is a lot of projects getting put on hold. A lot of projects delayed, and then finding themselves in a new set of code requirements, or maybe the municipalities have upgraded their bylaw requirements relating to the step code. And now they're in a situation where the design teams have to kind of struggle to upgrade or retroactively kind of update and improve the performance of their designs, which is not an easy thing to do. It can be really really quite challenging. And the other thing we're seeing more and more of is financial or funding institutions or organizations uh, increase requirements for performance, energy performance in particular, or sustainability generally, and reward higher performing buildings with better lending terms or higher lending amounts. So we see a lot of developers kind of going back to client or to design teams and saying, well, look, well, what do we need to hit step code for, or whatever their lending requirements or lenders require for them to borrow the rates that they require. So yeah, seeing a lot of that as well. So our approach, my firm's approach anyway, is the opposite, in that we start at the highest level of the step code, the best assumptions that we can come up. We always start with all electric. for apartment buildings, for houses. And then we work back from there. So, obviously our clients have requirements as well, which we always hit or very much try and hit or get close to, specifically relating to their budgets. And often we have to fall back on the performance of buildings in order to meet those budget requirements. So we might find, for example, that we need to reduce the level of insulation, or we need to reduce the performance of the windows or mechanical systems or whatever else. But it's a lot easier to do that if we're working backwards. So we're starting off with the details and the assemblies and all those connections and everything else. We're starting off at the point of being at that highest performance level and working backwards from there. And we find that to be a much more positive experience and much less damaging in terms of project timelines and consultancy fees and everything else if we have that approach. Um, yeah, I'd just say our general approach as a firm really is to see those higher steps um, and those higher performance requirements as really as the norm. As this is just what we do as standard. And as I said, if we need to reduce back and pull back from there, that's easy. Yeah.
Thank you, Nick. And now moving on to the role of electrification and heat pump technology. So really focusing on mechanical systems here today. Again, for some context, BC has the cleanest electricity in Western North America, and electrification is the fastest path to decarbonization, especially in BC's low carbon grid. So fossil fuel-based systems like natural gas, propane, oil significantly increase greenhouse gas emissions. And the zero carbon step code then rewards all electric designs with the lower greenhouse gas threshold. So talking about future proofing, eventually all electric buildings will be compliant long term also as regulation tightens. So it's important to look at that now because 2032 is kind of around the corner a little bit. So investing in gas infrastructure today could lead to also expensive retrofits tomorrow. So we have to think about, thinking a bit ahead. And there are a lot of opportunities, and Brian will speak to that as well, to integrate electrical systems as well with solar and resilient building strategies. So it's all part of future-proofing our buildings. So when we talk about electrification, we're just not talking about mechanical systems, we're talking about a shift in how we design homes that are efficient, resilient, and beautiful to live in. And in practice, those are the type of mechanical systems that you'll be able to see, or you'll see more and more of. And again, the goal number one is to reduce operational carbon and to meet the zero carbon step code targets. And there's lots of options to get there. And Brian, do you want to take over from here?
Certainly, I can talk about a few things. First, I'm going to mention I don't normally talk about heat pumps and so forth in our day-to-day, unless someone stuck a line set through a wall that requires a rating. But with my background in mechanical engineering, talk about heat pumps and a few of these systems. I want to go to the next slide. So so how do heat pumps work? Just a general refresher on what they do. They're a mechanical system. On the left here, we have a wonderful picture of a window air conditioner that I found. It looks like it's supported on 8 tracks or VHS tapes or something like that. But it demonstrates what the basics of a heat pump. So on the right side, we have a diagram of the full cycle system. On the left, we've got this red squiggly line, which represents the heat exchanger on the hot side of the heat pump system. So that is what you can see in the picture, as was circling there, is this copper tube and aluminum fin assembly on the outside. And there's a fan that blows air over this assembly. And then going from that red squiggly, we go into the number 2 here, which is called an expansion valve, which just allows a change in pressure in the refrigerant system. And it turns blue or cold This is where it goes cold. And then we have, which you can't see in the picture, is a heat exchanger that also has a fan that blows air into your house, your bedroom, or wherever you've put this into the window. And then the fourth step in here is a little pump. So it takes the refrigerant and it increases the pressure up. And with that temperature or that pressure increase, we have a temperature rise. So in the basics of it is we have this material, a fluid called a refrigerant that's inside the system. And that can be a variety of different things. If you have an old car, you might have heard of old R12, which is depleting the ozone and so forth. And the newer cars have R134A, and we have the new systems at 410. And now they're talking about using propane, which they call R209. There's also CO2 systems and ammonia type systems. Nearly all the ice rinks around the country are run on ammonia to freeze the ice and so forth. And the main criteria that they choose for refrigerants is that it evaporates at a low temperature and a pressure, that it condenses at a higher temperature and a high pressure, and that the temperature increases or changes with the pressure in the system. So if we start at number 4 here with our pump, it takes a low pressure refrigerant, which is a gas, and it increases the pressure. And in that increase of pressure, we get a temperature change. So it might come in at the bottom into the pump at, say, minus 10 Celsius, and it will come out at, say, 60 Celsius. So if you have, in the heat dome, we've got 45 degrees Celsius temperature outside, but the refrigerant's at 40 or 60 degrees, well, we get a heat transfer into the air that gets blown over this heat exchanger. And then that causes the refrigerant to cool down, and it becomes a liquid. And in that phase change, we get a large absorption of energy into the refrigerant. Well, in this case, we're rejecting, sorry. We've got high temperature refrigerant ejecting heat into the lower temperature air. My apologies on that. We're going to the other side, the other way. So we're actually cooling the refrigerant in this case. And then when we get to the number 2 here, the expansion valve, this allows our high pressure to reduce down to a low pressure. And with that, we get this temperature change. So you say I might go down to minus 10 Celsius here. Now on the inside of your house where you've got 30-degree temperature, blowing warm air over the heat exchanger, we're warming up the refrigerant and causing it to evaporate. And again, the phase change embodies a lot of energy in the fluid, and then it just goes around. So that's the basics of what we typically see as an air conditioner. And in here, I put a couple energy values. Oh, we go back a slide here. So on the right side on the cold circuit, say we're taking 2 kilowatts of heat out of the air within your room. Now we're moving along to our compressor. We're adding 1 kilowatt worth of heat energy into the refrigerant. And then on the hot side, we're rejecting all of that heat energy, the 3 kilowatts out into the atmosphere. So this is great for air conditioning. And if you really want to have a cheap heat pump or warm your house, you take your window air conditioner and you turn it around in the window. And you have the hot side on the inside and you cool the outdoors. And that's how a heat pump works. Except for instead of doing that with your mechanical systems, there's a fancy little valve that changes the direction of the refrigerant in the system. So I'm going to go to the next slide. So in this great little diagram from Natural Resources Canada, we're showing the refrigerant moving in down from the inside, going to the bottom through the expansion valve to the outside heat exchanger. Now, this outside heat exchanger typically will be what they call a air source system, where you're running air across the heat exchanger. But you can also do what they call ground source systems, where they run a secondary loop with water in the ground and transfer the heat that way. And you could also use a river or the ocean and different things, but air source is the very typical, easy solution that we have out there. So in this case, yeah, we've got the refrigerant coming in at a low temperature, low pressure, the outside air, our refrigerant's at say minus 40. The outside air is -20, so we're warming up the refrigerant. It becomes a gas. It goes through this thing, this fancy valve called the reversing valve, into the compressor, gets pushed up in pressure and temperature. And inside, where we've got, say, 60-degree refrigerant now, warming up our 15-degree air inside the house. And on the inside, we have different options for this as well. You can do a water type system, like I have in my house, where we have radiant heat in the floor. So you can use this to heat that water in the floor. You can also use it for domestic hot water heating as well, though these systems can be, depends on the exact physical properties and the type of system. So in that case, the hot gas gets condensed down, and we go through the cycle all again. So typically, for the outside, you will see these units on the upper right corner, particularly the one on the left. Very, very typical type unit. Inside these are the compressor and this outdoor heat exchanger, and they blow air through this. In the middle here, we've got the indoor units. There's a typical wall-mounted cassette on the left, and a ceiling-mounted cassette on the right that blows air through across that heat exchanger. And then on the bottom here, we have our most favorite hotel PTAC unit, which is a combined indoor-outdoor unit, and they're typically very noisy and so forth. There's a lot of newer ones. I've seen them on some new projects where they're very decent to deal with. They're quite nice. All right, next slide. So here we have the opposite system. You can see this reversing valve in play here. It's just changed the direction of the fluid flow through the system. So when we're doing air conditioning in the summer, that goes the other way. So now we have the cooling on the inside, where we're cooling air inside, and then we're heating the air outside of the house or the building. And on the right side, we have our typical furnace type system. This particular one is gas fired with a cooling coil on the top, but you could, now if you add the reversing valve in, provide heat through this heat exchanger up on the top instead of running the gas. And you can have the gas as a backup heat per se, or oil or electric is also a common option that is done with these as well. Okay, next slide. So electric hot water heat. On the left, we have a very typical immersion type hot water heater. Behind these sort of plates on the middle of the cylinder are elements that go into the hot water that turn on and off to regulate the temperature in the tank. In the middle, we have a heat pump version where there's a heat pump at the top, and it has immersion heaters as a backup. But it also has that heat exchanger within the tank in the water to heat it. And on the right-hand side, we have a commercial industrial centralized unit, which is just a very large version of the heat pump system. You have a compressor and just a lot more refrigerant and larger heat exchangers. That's really what it comes down to. Okay. So electric cooking is a way to get rid of the pollutants that come from cooking with gas in your house. We've got a few options. The old school electric burner on the left, something we've seen a little bit sooner, or sort of in between here. We got these radiant cooktops, which have a hot element in the middle that heats your pot up and will take any type of pot. And then when we have the newer version, the induction cooktops, and these work on electromagnetics, and they use your pot actually as part of the heating system. And this is why some pots will work with them and some do not. Typically, they require a certain amount of steel or iron in the bottom of the pot, and through the magnetic resonance that goes back, which is a frequency to change the electromagnetic field, it moves the atoms in the steel, which creates heat and heats your food. I have heard recently that they have some new units coming out that will detect and work with aluminum pots as well, which is interesting. But these are very nice. We have one in our house for the simple reason that you can boil up water and you can pretty much take the pot off and stick your hand right on top of the cooktop and you won't burn yourself, unlike with the radiant or even the old school electric burner. It's a little bit safer mean, the pot's still hot, but that's the part that's hot. And the glass gets hot from the pot and not from a burner or electrical heat source below. Okay. So then in some ways we deal with the electric power, and we're lucky enough to have hydroelectric just spinning the old power generation all the time. But other places are not. So how do we deal with the peaks and lesser demand throughout the day? Or say we want to use all our electrical power at night. Well, solar, of course, doesn't produce at night. So we have battery systems that have been more recently put into place. As I understand it, Texas has had a lot of good results using battery systems in their peaks and valleys of their demands the last couple of years in doing so. They, of course, have some challenges with the batteries. There are some older school methods of a similar approach, these pumped water storage systems. I understand we have one here in the Niagara area in Canada, and depending on which article you look at, there's somewhere between 30 and 45 in the States, where you have an upper reservoir and a lower reservoir, or it could be a river at the bottom. But when there's low demand times, the electrically will pump water up into the upper reservoir, and then during peak demand, they'll generate power by letting the water come down to the lower reservoir and push that power into the system. And we have our favorite these days, our electric vehicles. I had a picture of a Tesla on fire, but maybe that was a bit too much. We have a great new VW van here, it seems, on the market, electric out there, which works great with our clean electric system, our power system that we have. So, great.
Thanks, Brian. I actually saw one of those in front of my apartment the other day, and I was like, oh, they look great.
Excellent.
Now moving on to some case studies and practical applications. So how does that work in real life? And I'll start by showing you a couple of projects, and then Nick will take it over with some of their projects as well. But first, this one, inlet view. So in Seychelles, also different locations throughout the case studies here. Fairly simple home that has a pretty lean design, met step 5 and EL4, which is the zero carbon step code. So it is an all electric design. Had a really good air tightness. Met EL4 with electric baseboards, Lunos HRV, and a heat pump water heater. And for those that think that this is happening in the future, like, no, this was built in 2023. This technology is not new, and it will I think only become more cost effective as more and more people start to use them. For sure, the heat pump water heater on this project was one of the most costly items for mechanical systems, but it also worked really well in the space, and in order to meet the goal of the client, which was to be all electric from day one. So that was built in 2023.
Actually, Elisabeth,
yeah,
if I can interject momentarily. If you
of
go
course.
back, there's one item I was going to talk about that I think people might find helpful. If you go back to one of my first slides on the first slide on the heat pump, I just want to talk about there we go, the advantage here and the ratio. So in this case, if we're using the hot side to heat our house, and we're taking 2 kilowatts of heat out of the exterior air, and we're putting in 1 kilowatt of heat in the mechanical system, we're getting a total of 3 kilowatts out of heat into our house. So this would typically be a ratio of the input versus the output. So we've got 1 kilowatt in and 3 kilowatts out. So we get a 3-to-1 ratio in this case, based on these numbers here. And this is the big advantage. So you could have a baseboard heater just pumping away at 1 kilowatt of heat into your room, or you can use this more complex mechanical system to get 3 kilowatts for your 1 kilowatt of input. So that's the big advantage using heat pumps. Sorry, I'll leave it.
Yeah, no, really good point, Brian. And that's the reason why, even though baseboards are more cost effective to install and they are a cheaper system, overall in the use of the building, a heat pump will be more cost effective just by using less energy to have an output that is the same for keeping the temperature. moving on to this project that was on Bowen Island, same a larger family home that met step 3, and that was all electric as well. That had a system like Brian was mentioning, the air to water, because they really wanted inflow radiant, and also had an integrated heat pump water heater. So that's one of the first ones we saw that everything was integrated. That was built last year. Again, a system that works well in our climate here, and one of the first ones we saw that everything was integrated, but they do exist. And then the Phoenix House, so a project that we are working on with Nick and his team, where we from the get-go, again, like in the design phase, it's funny because we should have had Nick the floor plan where he showed the little nook for the heat pump, because Nick in the very first design and geometry of the house already had the spot for the outdoor unit of the heat pump, and us as energy advisors seeing this right away on the plans, I was like, yes, this is good because we'll for sure have a heat pump. And in the conversation with the homeowners, also really wanted to be all electric from the beginning. There's a lot more to this project that we can talk about in terms of embodied carbon and materials and choices, and this project won the embodied carbon awards last year. But purely here on the topic at hand today, it meets step 5 and EL4, so zero carbon step code. We are doing the blower door test next week, and hoping for, I'm being conservative here with the air tightness of 1, but really hoping for well below that. And a fairly simple mechanical design. We had a mechanical engineer onboarded as well for this project for sizing of ducts and efficiencies in the system and how they run. That's one thing that as well I'll mention in projects, is that having a mechanical engineer or right sizing mechanical systems is a way to make sure it is cost effective. So we have often seen a lot of mechanical systems that are oversized, mostly because well, either there's no calculations being made, so it's just like, well, we've been installing this 3-ton system for 20 years, so we're just going to keep installing them. But as our buildings become more energy efficient and retain heat so much more, or cooling in summer, but like as they retain their temperature so much more, we don't need such a large system anymore. So that's one of the key things as well, is having best practice is having F280 calculations done for sizing of the mechanical systems, and that is best done by either your energy advisor, energy modeler, or the mechanical engineer. Some HVAC contractor will do it as well, but we have often seen as energy advisors that their assumptions are slightly different than ours, and we have a better understanding of the high performance features, insulation values, window values than them when we run the calculations. So just a quick note on that. F280s should be required for all. They are officially in the code actually, but not enforced yet by local governments, but should be required for all mechanical sizing. And last thing before I pass it over to you, Nick, is there will be a site tour coming this summer for this house, a couple of them actually. So if you're interested in seeing this house when it is completed, then feel free to reach out.
Yeah, I think the Phoenix House is certainly the most progressive project we have in the office right now. It's we really had to rethink how we design with this one. All our assemblies, all the products we were using, different insulation, different everything. So no, it's a really interesting project, really exciting, and it's kind of paving the way for the way we build in the future. And we're already, as a firm, we're already implementing a lot that we've learned from this project in larger scale projects. So our wall assemblies and some of the products that we're using. So no, it's a really exciting one. If you can't make the open houses, there's a dedicated website, there's an Instagram page, there's all sorts that you can jump on to follow this project, and then everything that we're learning on it. What we got next? Yes, okay. So this house, actually caveat, this is actually my house. This was finished over 5 years ago now, and the reason I've included it is partly just to explain some of the all electric features of it, but also to just discuss how far we've moved as an industry since then in the last 5 years, and how quickly our approach, our mindset as professionals has changed in terms of where we're putting emphasis and what we're focusing on. So yeah, this house finished 5 years ago as a certified passive house, all electric. It achieved very tight air tightness 0.3, less than 0.3. It was heated by a mainly electric heat mats, but also a mini split system that heats as well. In hindsight, I would have known what I know now. I would have gone with a full heat pump system and maybe only done heat mats in the bathrooms for comfort. Obviously very high performance, high efficiency HRVs, and a large sand and hot water heat pump system in that house. We learned a huge amount from this. I probably learned more actually from living in it than I did from designing it. And we learned a lot designing it. Back, I think we designed it sort of 6 or 7 years ago, and it was back when we knew less as an industry about these high performance buildings. One of the big things we learned was the difference between energy modeling and the reality, and understanding that energy modeling is obviously incredibly important and incredibly complex, and we need it to inform our design work. But obviously the reality is sometimes somewhat different, especially when it comes to overheating. And obviously energy modeling can only use averages, climatic averages, in its workings, and the reality in Vancouver is anything but our weather here is anything but consistent. So understanding the differences there, and obviously trying to combine everything we're learning from like Elisabeth's incredible work with the kind of just the old school theory that we've always known about kind of producing healthy homes and efficient homes, and trying to come up with a design that works for both. So what we learned on that project and got incorporated not just in the future sort of projects that we worked on at this scale, but also larger scale projects. We use a lot of the assemblies we learned on that project and incorporated them in bigger projects. But we mainly work on larger scale projects, but we do these kind of these smaller homes as more experimental learning opportunities, let's call them, passion projects. So this is a single family house, coach house plus coach house in Amor. Again, all electric, Step 5 VL4, net zero. We probably won't get this one certified, but we're aiming for net zero. It's what we're learning now is to integrate these high performance components into our design. So you might be able to see on this design there's some sort of vertical cladding there that looks like open cladding. Now, part of that is a louver to solar shade those windows. So when in the summertime we can, like a Mediterranean style exterior louver, we can provide solar shading to prevent overheating in the summer. But the other side of it is actually hides the fan units for the heat pumps. So we've integrated those units into the design to make them more seamless, rather than just sticking it on the roof or sticking it out the back garden or whatever. It's an integrated element. So yeah, it would all be heat pump. We'll have some electric heat mat backup, probably in the bathrooms, maybe in some key locations in the living areas so you get that feeling of comfort. And then you can use those heat mats if ever the heat pumps were to fail. We're hoping that wouldn't be the case. I've certainly on my house, we've never had an issue with in the last 5 years with the heat pumps failing. But it is Vancouver, and I saw a question there about in colder climates relying on heat pumps. So we'll address that towards the end of this seminar. This project, we'll quickly roll through these. This is our first multiplex in Vancouver, again, all electric. We're benefiting from that 19% area density uplift that you get for going net zero. You can go passive house or net zero. All electric. We've incorporated something, you can just about see it on the right hand image there, where we've got like a setback, a niche on the side of the building. We did the same thing on the Amor house, where we're hiding our heat pumps within that niche. So we're kind of incorporating them into the design, the fan units, exterior fan units. This will be all ducted mini split units and a centralized heat pump for hot water. Yeah, this is part of a larger scheme. This was a new build, sort of replacement building. This project will be largely using Innovas or Innovas. Still not totally sure how to pronounce that, even though we've installed a lot of them now. The PTAC units, wall-mounted PTAC units. Yeah, 20 unit social housing. But the next project is the second half of the project. So the next slide. So the larger portion of the project is actually a series of energy retrofits on existing social housing buildings. These two here are 36 units in total. We're basically bringing up to beyond current code standards in Vancouver, so step code 3, and electrifying them. So they now all have individual PTAC units, and you can see the Innova units. Hopefully you can see them underneath the window there. Very, very beautiful looking units just mounted on the wall, that deal with that heat and cool those individual studio units. We've got centralized hot water heat pump system that works for the entire building. And also through this project, you can see the difference before and after difference there. We've put in new air barriers, exterior insulation, added exterior insulation, and new cladding. So the building looks like new. We've given it not just a new look, but also longevity for, we hope, another 50 years, to expand the length of those buildings. We've got a lot of projects like this now. They've got I think seven of these projects, the largest one's 160 units. That we're retrofitting now, and we see that as a huge move forward within our industry to not just rely on building new, but also retrofit. And just lastly, last slide here, most of our work is at this scale, this mid-rise scale. Apartment buildings, these, as I said, we start off at step codes 3 or 4. And step code 4, and we work back from that if we need to. We start off at all electric, and we work back from that if we need to. So the space heating, there are other options, but for all of our projects, they're kind of a given. They're all the same. We have mini split systems in each unit. They're either ducted or they're just wall mounted in the living rooms. And then we have baseboard heater backup. So we rely mainly on the mini splits, but then the baseboards are there to assist. So that's kind of a given. We don't generally have any kickback on that approach. But the hot water is up for grabs, really. I mean, we've got all sorts of different options in the different buildings we're working on. Probably most of all is in-suite electric immersion boilers that Brian talked about earlier. So every suite gets its own boiler, all electric, obviously. But they're cheap to install, but costly to run. More costly than a centralized or zoned heat pump system. What we're finding is that we aim for the heat pump system on the roof, centralized system for hot water. But often because Fortis get involved and often offer rebates for gas systems, we find ourselves kind of leaning back towards the gas hot water, unfortunately. But the good part is that we design them in a way that they can then be converted back to heat pump in the future. So with little work, it's just a case of converting or upgrading that rooftop equipment. Everything else stays the same. And then ventilation, every unit gets an ERV. So those for those apartment buildings, they tend to follow in the same approach, the same systems. So that's all from me. I don't know, Elisabeth, you have a bit more to say here.
No, that was great, and I see that we are almost at time here. I see. Thank you, Brian, for answering the questions in the chat. I think we've left no question unanswered. So just key takeaways here. In the design, fuel choices matter, as you've heard here from Nick. It is important to future-proof our building, and natural gas systems will struggle to meet the greenhouse gas limits just because it is natural gas is just a higher carbon fuel. So we are moving towards electrification, and if designed early on, then those mechanical systems work well. They are is not the next point, but it's not new technology. They've been tested and approved for many years. If you think about it, a heat pump is like a fridge in the system. So the physics are the same. So, the technology is not new. And it's important to start designing with mechanical systems in mind. So investing early in mechanical design with a professional, bringing your energy advisor or modeler early to add the most value, and also to avoid redrawings and redesigns, because that's really painful. We know it all. And so it is mechanical systems are now an early design decision. And as Nick was mentioning, we know that the one good thing with the step code, energy and zero carbon step code, is that we have the targets. We know where we are heading, so we can plan accordingly and start designing for those buildings now with the technology that we have today. If you want to add anything, Nick or Brian, feel free.
No, thank you very much, Elizabeth. I think we started 5 minutes late because we were waiting for people to arrive there. So I think we can continue on a little bit. We do have a few questions here, but I did want to just mention before that about just the changing direction of our industry. And I think we're yeah, as we learn more and more about embodied carbon, and as we move towards electrification, especially in Vancouver where it's mandated. I think we're going to find ourselves focusing more and more on embodied carbon and these all electric buildings and the systems relating to them just being the norm. And I think we're finding that in an all electric building that embodied carbon is the most serious thing that we need to be the most impactful aspect of the carbon cycle that we need to focus on. I don't know if Elizabeth, you want to comment any more on that?
I mean, I could spend another hour talking about embodied carbon, so we might not want to go there. Yes, the materials that we use as we make our buildings more and more energy efficient, we tend to use a lot, like more insulation, triple glazed windows, etc. But it's important to think that those also have an impact on the environment. So embodied carbon, which is all the emissions associated with raw extraction, manufacturing, processing, construction processes, that it's important to start looking at those, because in our clean it is in this context of BC, but in BC with a clean grid, an all electric building will emit very, very little greenhouse gas emissions during its use. So it is becoming now more and more critical that we look at the materials that we use to make those buildings more energy efficient, as well as refrigerants. That's another big one. The global warming potential of some of the refrigerants is really high. And so with refrigerant leakages, we also see greenhouse gas emissions associated with that can be quite high. Very little data available, but a lot of bright minds are working on this and showing that we have to pick out a refrigerant that has a lower global warming potential, and again, efficiency in all terms, in the design, in the mechanical systems, making sure we don't over engineer and over design for all of those systems.
Yeah, the refrigerants is an interesting conversation, particularly if they're looking at propane as a refrigerant. You don't want to have a leak in your basement with the refrigerant, i.e. propane leaking into the basement. That's a big fire risk. So something to be concerned about. But there are other challenges, of course, with every refrigerant, where you use CO2 and ammonia are both a big health hazard for the asphyxiation and so forth. So yeah, everything's a trade-off.
Everything is a trade-off. Part of the design and like balancing all of those key components. There is a question, I think, for you, Nick. What are the key points for designing gas systems for future conversion to electric?
Yeah, to be honest with you, that's more of a mechanical engineer question, but I think the key thing is to have the systems in a place where you can accommodate a location where you can move them and accommodate new equipment. So we try and put, especially on the larger mid-rise buildings, we try and put it all on the roof so that we can easily crane off existing systems and move in and install new systems. You don't want them confined to areas where you can't move, either can't actually get the equipment out, or which happens more often than you believe, or install new equipment. So that would be one. And yeah, I think with the hot water, it's with all the equipment being on the roof and just pipes being below, it's an easy switch. There is another question here that I do want to address from Mika. Also a couple more actually, which is about building in the north and in colder environments, and there's been a couple of other questions as well about the reliance on all electric or the reliance on heat pumps, because we have all heard stories of heat pumps failing. And there is, of course, a big cost item here because especially building in areas where electricity sources aren't, or electricity supply, sorry, isn't reliable. And obviously, the obvious solution is to do gas backup. But there is obviously a cost involved in that, which is a pretty serious thing. So no, it is a factor that we do need to consider. And Brian, I don't know if you can talk to why at these lower temperatures we're finding some heat pumps. When you get -40 or below, why some of these heat pumps are failing.
I can't really speak to the failure, but from an operational point of view, it just depends on the type of refrigerant you're using and if the all those materials have a certain band or sweet spot where they work well. So if you're trying to cover a very large temperature span, I guess you could do it with a couple different types of heat pumps with different refrigerants to work at different temperatures. But uh, yeah, those really cold temperatures are probably just outside the band of where this equipment has been designed to operate.
Yeah, so from our point of view, what I can say, like on our projects, especially the social housing projects, some of which have seniors in them, where more vulnerable residents. What we're doing, so I showed you a project, an example there with Innova system, a wall-mounted PTAC heating cooling system. When we're installing those, we typically do include baseboard backup. So baseboard heaters aren't expensive to install, so we'll put those in there and only use them upon failure of the heat pump system, because they obviously are a lot more expensive to run. But what we also do, what we recommend and kind of strongly recommend is that with those units, because in those buildings like that, with a complex like that might have 200 or 300 Innova units installed within it, is to have spares. And they're really easy, those ones, to switch in and out. It's a sort of half an hour job to switch an Innova unit out for an equivalent. So to have spares on site, and also to have, if necessary, just standalone bar heaters, electric heaters that they can use just in an emergency. Now I've done it, obviously if we're dealing with a centralized system, it's a bit of a different situation because if you have a failure, it's going to affect everyone at once. But yeah, maybe something to consider.
And also one of the things that we've seen as well with like high performing envelopes is that even in case of a power outage, or that was the case I think in Texas 2 years ago, there was a passive house that actually could maintain the indoor temperature at a livable temperature. So like obviously if there's no more power and there's no backup whatsoever, if you have an airtight, well insulated home, the temperature will drop, but very little by little, and they stayed, I think, 3 days without any power, and it dropped from 22 to 16, which is still livable, right? Yeah, just put a jacket on, which is in terms of resiliency as well, something that we, I think, underestimate. But having a high performance building envelope will prevent some of the more risky situations, I think.
Right. I think we just finish on one more question here. Sorry, just flicking through the questions here, but there's a few questions that's kind of along the same sort of line, which is what are the some of the challenges we face with step code and zero carbon step code requirements, but also what resistance are we facing from clients, from design and construction teams about going all electric. I mean, from my point of view, that is the biggest challenge. It's persuading people to clients, consultants, contractors, trades to not just do what they've always done. You know, persuading them that there may be a better approach here. And for us, that's the biggest challenge. Like you do unfortunately meet some consultants that just want to do the same thing, copy paste, copy paste. and trying to change their minds on that and you know, persuade them to be more progressive. Yeah, persuade them to learn because
Yeah.
things are moving very, very quickly. As we said before, you know, the technology, the skills that we have as an industry is all moving very, very quickly at the moment. So trying to get everyone up to speed with that for me is the biggest challenge. But
Yeah, and yeah, I agree with that, Nick. And I would say also getting your team, like getting a team that you trust that will keep also track of all of those things happening, because like we can't know it all. Like even in our space, like this is, you know, energy and carbon, this is what we do every day. Like it evolves so quickly. Like I wouldn't expect our clients or even builders or like Edda to understand and know it all, right? Like we have to rely on each other as well, and understanding where and who you can ask those questions is important, which is part of sharing the knowledge that we're sharing today, and those seminars that you're putting on, Nick, is sharing the knowledge and as the industry evolves so quickly.
fantastic. Yeah. Thank you very much to Elisabeth and Brian. I think we're at the end of our time here. Thank you also to Ori who stepped in to organize this for Shannon, who unfortunately became ill recently. So as I said, we will be we'll send out an email to everyone here actually and send a link. We will be putting the recording of this seminar up on our YouTube channel. And we hope to see you again at the next seminars. So thank you very much.
Thank you.
Excellent. Thank you.